So our applications of derivatives topic today is just rates of change. And so when you get a model of something, in this case they've got a number of bacteria in a colony, and they've came up with an equation to model how many bacteria are in this colony after T hours. That gives us an equation. Now, we can find a rate of change, because that's just what a derivative is, at any point. In this case, we can find the rate of growth. So in these application questions, you're going to get one equation, and then they're going to ask for, like, what is the rate of growth, rate of different things, and you'd be like, okay, that tells me I should take my derivative. And what that derivative will tell us, so here it's going to be 60 plus 15. After 10 hours, plug in 10, you would get 75, and then we can use our units here. And what that's telling us, that after 10 hours, this colony is changing at a rate of 75 bacteria per hour. So you could do an estimate and say, I would expect there to be 75 more bacteria in the next hour. So this is what this is telling us. The derivative, this isn't exact. We can actually find out exactly what it is if we go to our original equation and say, how many bacteria are there after 10 hours? Then you plug it in, you get 300 plus 150, 450, 1250, and then we could check how many bacteria there would be after 11 hours, and again, go to our calculator. And we notice that this has increased by 78. The derivative gives us that estimate. But that estimate right now, the derivative right here, is finding like an instantaneous rate of change right at 10 hours. At that moment, it was increasing at 75 bacteria per hour. So we could use this to say, I would estimate that from hour 10 to hour 11, it would go up by 75. Pretty good estimate, it went up by 78. Why did it go up by a little bit more? It looks like this colony of bacteria is increasing faster and faster and faster. And if you think about it, it's a parabola. It is increasing faster and faster and faster. So 75 was a good estimate. We can find out exactly that it increased by 78. But this caused us to plug in two things into a more complicated equation. In this example, the derivative was a simpler equation to plug in something once. So it gives us an instantaneous rate of growth, but it also gives us an estimate for how we could expect to see what would happen over the next hour. Show that the number of organisms will always be increasing. So if we look at our derivative, which was 6t plus 15, I'll write it out again here. And what was our n of 2? There's our derivative, but we set our derivative equal to 0. Now, negative 15 over 6 is actually lower than our domain, because our initial amount would be at times 0. So often in these equations, since it's a real-life equation, you have to think about the context. Yes, the only number that is on your critical values is 15 over 6. Maybe I should change this even to a different color, just to imagine, hey, all we have to think about is from times 0 plus. And if I plug in anything bigger than 0 into this equation, I'm going to get a positive number, which shows that it is always increasing. You don't have to plug in, even though you know this would be plus as well, you don't have to plug anything into that part. You don't have to plug anything into this part, because all of those things are not part of the situation, because they go back in time. So from time 0, this thing is always increasing, which then makes us think about our model. Is this realistic? Would it be possible for bacteria to always just increase and increase and increase, or could there possibly be some problems, right? Some realistic problems. They're probably going to run out of food, right? Once something gets too big, it runs out of food. So I'm just going to say no. That's short. Probably not, but no. Because they're going to run out of food, so we probably have some sort of thing. If we look at populations, lots of population growth is increasing, 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 and then it gets into a branch of mathematics called chaos theory, because things run into problems. It goes into a state of chaos where a bunch of populations dying, going up and down, and then it stabilizes and then gets back into its regular pattern again until it runs into another catastrophic situation and has to figure itself out. It's going to be warm today, which means they're coming. The mosquitoes are coming. I think mosquitoes are there so that we good, it's winter again, just for like a day. And then wish it was summer. So I like this question because I can imagine, why would someone want to make a controlled laboratory experiment with mosquitoes? But we've got an equation for population. Find the growth rate. So anytime a question has this growth rate in it, you know that you're going to be wanting to find your derivative. So first thing, we've done lots of derivatives. Test yourself out. Do the derivative for this one. See what you get. And then once we got that equation, how did you do on your derivative? Derivative of E stays by itself, but then this one has a chain rule, so you also have to multiply by 0.09. I don't know if any of you simplified it, but if you did, you'd get 22.5. And then once you get your answer, you'll have to look at these questions because they have units. We are measuring mosquitoes per day. So on day 5 to day 6, you could expect an increase of 35 mosquitoes. Again, I'll get you to start this one and try this one on your own. I'll put the answer up in a second. So there's our derivative. And at 10 minutes, we plug this in. And you get negative 2.436. And our units here are degrees per minute. So it's going down about 2.5 degrees per minute. And this is actually one of the places that exponential functions get used. If you have a warm object that you bring into a cooler room, it will start to cool. It won't stay at that temperature. And its rate that it cools off will follow an exponential equation. So in this example, if we put in time at 0, e to the 0 will be 1, 90 plus 34. This object is 124 degrees. Not a good idea to pick it up. Okay? At 10 minutes, it's going down at 2.5 degrees per minute. So we could look at what is the actual temperature at 10 minutes, how hot is it? We could get an idea, could I touch it in 10 minutes after that time? Probably still not. So still would be quite hot, but this is an actual application of exponential functions. It follows, I think it's called Newton's law of cooling. And in IB classes, I've had some students do IAs on Newton's law of cooling. Usually it's more exciting to use like dead bodies and find out how warm they are and try to figure out, based on how warm the body is now, when did the person die? And that's actually one application of that. So a student looked at a whole bunch of different ways you could determine, using forensic, finding a body, when was the time of death, based on the temperature.